This is the operation we made for the ALU, which is the comparator. This is for the 1-bit converter. We used the graph on the textbook and used all those logic gates. And then we create a 4-bit comparator, which is just like the full adder. We have compared each bit and like A1, A2, A3 here, and we assign equal if they are all equal to same, and greater if the first bit is greater or second bit is greater, and then the last is just not equal, not greater. And then we have our temperature sensor code. So the temperature sensor code is basically broken into two parts. The first part is to read the temperature from the sensor. We also have a clock here to register time. The second part, which is here, is the 7-segment display. We assign the bit of the value into the 7-segment displayer.
So here we have the code for the guessing game that is used on FPGA. So here we load the seeds, which I use for the LFSRs to generate the Swiss random numbers. And here we call those LFSRs with the seeds. And here we assign the LED colors to whether or not guess is greater than, less than, or equal to the secret number that we generate. Now inside of LFSRs, we have 4D flip-flops and muxes, which basically just help us load the seeds into the flip-flops for the LFSR. Now inside a D flip-flop, we have clock signal and a reset signal. We kind of use the button as a clock, so when the user pushes the button, the next number comes up. So there's that, and that's the guessing game. So the guessing game on FPGA worked really well, but we couldn't figure out the temperature sensor because most of the documentation on it was in VHDL, not Verilog. It was difficult to figure out.
Yeah, that's what we got. And we also got the comparison in ARU, which works good with other segmentation display.
So on this FPGA, we have 5 bits of opcode, 4 bits of A, and 4 bits of B, from most significant bit to least significant bit. Now we added 8 new operations to the ALU. Right now, this operation is A equals B, so it's output a 1 to 7 segment display if A is equal to B, and 0 otherwise. So you can see A is 7, and B is 7. When I change it, B will equal to 0. Next operation is A doesn't equal to B. So we have, right now, A and B are equal. If I change it, it'll output a 1 to 7 segment. Next is A is less than B. Right now, A is less than B. So right now, A and B are equal. If I change A to be 6 and B is 7, then I'll put a 1 and 0 otherwise. Next is A greater than B. If I change B to 3, see, this makes A 7, B is 3. That'll make A greater than B equals true, which will be 1 to 7 segment display. Now we have A shift A to the left 1 bit. So right now A is 4. Shift 1 bit to the left makes it 8. If I go A shift right, which is this operation, this will make this 2. This will make this 4, 2. Now this is B shift B by left 1 bit. So right now B is 3, shifting 1 bit to the left makes it 6. Now this is B shift right. Shifting B to right by 1 bit makes it 1. Okay. Now we have this guessing game. Basically, there's a secret number that the user doesn't know. When the number is lower, when A is lower than the secret number, this will make the LED light blue. If I make this secret number too high, the LED will be red, and when it's just right, like the porridge, the output will be green. And I can press this button, and that'll change the secret number. So now the secret number is 8. Change it one more time. Probably 13 or something. Nah. There you go. Secret number is 13 now.